Hi everyone, welcome back to our walkthroughs. So on this very third question, we have this RLC bandstop filter. So as we have seen in the lecture, to construct a bandpass filter, we can cascade a high-pass filter along with a low-pass filter. We can also make use of a capacitor, an inductor, and a resistor to actually construct a bandpass filter. What's going to happen if we change the order of the resistor, the capacitor, and the inductor? Let's take a look at this question. As always, if you want to think about this problem on your own, feel free to pause the video and 3, 2, 1, unpause. So for the first part, we want to write out the transfer function of the circuit of unknown behavior. Okay. So we know that the impedance of a resistor is R itself, the impedance of a capacitor is 1 over j omega c, and the impedance of an inductor is j omega L. Okay. So in phasor domain, we have seen in the past that this is just a voltage divider. And so the transfer function of this circuit is just going to be h of j omega being equal to v tilde, v out tilde, over v in tilde, which is then just equal to zc plus zl over zr plus zc plus zl. Okay, so just plug in the values over here. 1 over j omega c plus j omega l over r plus 1 over j omega c plus j omega l. Okay. And then we try to simplify this expression. For the sake of simplicity, we're not going to be multiplying both sides of the fraction by j omega c, but rather we're just going to write 1 over j as negative j. So that's going to be equal to j times omega l minus 1 over omega c over r plus j omega l minus 1 over omega c. Okay. Now for part B, what is the magnitude of the transfer function? As we have iterated a couple of times in the past, the magnitude of a quotient is just the quotient of the magnitudes. So this is just going to be equal to the magnitude of j omega l minus 1 over omega c over the quotient, over the magnitude of r plus j times omega l minus 1 over omega c. Okay, so on the top, we know that the magnitude is just omega l minus 1 over omega c, and on the bottom, just the square root of r squared plus omega l minus 1 over omega c squared. And that is our answer for part B. Okay. Now moving on to part C, we want to sketch the magnitude of this transfer function. So this transfer function, it has a magnitude. Let me copy this over. H of j omega, its magnitude is equal to omega l minus 1 over omega c over root r squared plus omega l minus 1 over omega c squared. Okay, so if we want to sketch the magnitude plot of this particular transfer function, we're just trying to draw the diagram with h of j omega, its magnitude as the y-axis, and omega as the x-axis. Okay, so we're just trying to draw out how the magnitude is going to change as omega changes, treating this transfer function, the magnitude of the transfer function, as a function of omega. Okay, so currently, omega appears in both the numerator and the denominator of the fraction, and this could be very annoying. To get rid of omega on the numerator, we can divide both sides by omega L minus 1 over omega C to get this. The magnitude being equal to 1 over r squared over omega L minus 1 over omega C squared plus 1. But there is an obvious problem to this approach, because omega L minus 1 over omega C, it must not be 0. Otherwise, you cannot divide both the numerator and the denominator by 0, right? But in that case, this would be an easy problem to solve because the numerator is simply 0. And so, in that case, the value, the magnitude of the transfer function would just then be 0. Okay? Now, to analyze how this value is going to change as omega changes, we first try to analyze the function, the behavior of the function f of omega, being equal to omega L minus 1 over omega C. The diagram for this function, it's going to look something like this. Okay, so imagine this is our omega, this is our y. This diagram is going to look something like this. Okay, how we get this diagram is sort of out of scope for 16b, but intuitively, if you think about it, if omega tends to 0 from the positive end, this term is going to be close to 0, and so f of omega is just close to negative 1 over omega c, which has the diagram something like this, right? So this is negative 1 over omega c. Whereas if omega tends to infinity, f of omega, since this term is just going to be close to 0, as c is a constant, we know that f of omega is just going to be close to omega L, which will have diagram this. Okay, so this is going to be L omega. And so our diagram is going to be similar to something in between. This is our f of omega. Okay. Now we want to consider how the magnitude of the transfer function is going to change as omega increases. So if omega increases, we can see from this diagram on the right that f of omega is going to be increasing. Okay. So we do a casework on the value of omega. So if f of omega is less than 0, that is, if omega L is less than 1 over omega c, then since f of omega is less than 0, f of omega is less than 0 over here, you can see that. That means its absolute value as omega increases is going to be decreasing, and so f of omega squared is going to be decreasing. Okay? Since this whole thing, f of omega, is in the denominator, we see that this fraction is going to be increasing. It's in the square root, and as a result, we see that the square root is going to be increasing. The square root is on the denominator, and as a result, this magnitude is going to be decreasing. Okay? It's going to be decreasing. Now, if f of omega is greater than 0, that is when omega L is greater than 1 over omega c, we should note that we never considered a scenario where f of omega is equal to 0, because in that case, we'd go down the second path, in which we just determine that the magnitude is 0. So if f of omega is greater than 0, as omega increases, f of omega increases. So f of omega, since it's greater than 0, it's when we take the square of it, it's going to be increasing. Okay. And now we look at this expression. So as f of omega squared increases, this fraction is going to be decreasing, which means that the square root is going to be decreasing, and so the whole fraction, the magnitude of the transfer function, is going to be increasing. Okay. So I should write it down. H of j omega is going to be increasing, and h of j omega here is going to be decreasing. Okay. So then we draw its diagram. Since we know it is a continuous function, that we know from part B, we wrote it out in as a fraction of two continuous functions, so it must be continuous. And we know it takes the value 0 at a certain point where omega L is equal to 1 over omega c. So we're going to draw the diagram over here. This is the omega, and this is the magnitude of the transfer function. At the point where omega L is equal to 1 over omega c, which is when omega is equal to the square root of 1 over LC, they're going to take value 0. At other times, when omega is smaller than this root 1 over LC, this magnitude of the transfer function is going to be decreasing. And when omega is greater than root 1 over LC, this is going to be increasing. Okay, so this is our transfer function. This is how our magnitude of our transfer function is going to look like as omega changes. I would like to say again, the mathematical maturity required in this question is is far more advanced than what you need to know for exams. And I mean, these are good. These functions, these are good to know, but not necessary for you to understand. Okay. Now, up to part D, when is the magnitude of the transfer function 0 and when is it 1? So as we've seen, the only point at which the transfer function can take on the value 0 from our diagram right here is when omega is equal to root 1 over LC. So when is the magnitude of this transfer function going to be 1? If you look at the diagram, it's pretty close to 1 at any given point other than this omega equals root 1 over LC. But if we actually look at the transfer function, the magnitude itself, like this equation, for it to be 1, to be exactly 1, this whole thing within the square root is going to have to be 0. And we know that r must be positive. So that's impossible. So you don't have any particular point that's going to reach exactly 1. Okay. But at any point other than omega equals root 1 over LC, it is pretty close to 1. So now on to part E. How would you describe the behavior of this circuit? Why do you think circuits with this type of circuit behavior are classified as notch or bandstop filters? And why is this specific filter called a resonant bandstop filter? Remove the S over here. Okay, so as we have seen in part C and D, we see that the magnitude of the transfer function is close to 1 for any given point other than this omega equals root 1 over LC, and at which point it's the magnitude is going to reach 0. Okay, so this is like exactly the opposite of the typical bandpass filter, right? So the bandpass filter, the magnitude plot is going to look something. As omega increases, it's going to look something like this, right? But in this case, we see that it just retains whatever signal outside of a specific range and cuts out the signal in the middle. So this is why this is called a band stop filter. And for the last question, we call a circuit resonant when the impedances of its components, they cancel out each other. So in this case, we realize that the impedance of the capacitor plus the impedance of the inductor at a given point, so that's basically when omega L minus 1 over omega C is equal to 0. So this is going to be equal to J times omega L minus 1 over omega C, right? And at the point where omega is equal to root 1 over LC, we see that the impedance of the capacitor and the inductor, they just cancel out each other. So that's why the circuit is called a resonant bandstop filter. And that pretty much concludes our walkthrough for question number 3 on the worksheet.